Okay, so in this video we're going to be talking about arrangements. So looking at different problems and the number of different arrangements we might be able to create and various mathematical tools that help us in that. As we start to deal with more complicated arrangements and selections in the next video, we also need to think sometimes quite clearly about the addition and multiplication principles. So am I adding together these number of options, or am I multiplying together these number of options? Really based on whether the phrasing of the sentence is really, do I want this thing and this thing to happen, or do I want this thing or this thing to happen? Okay, so let's work through the theory here. So let's just think about a couple of simple problems and then sort of generalize that a little bit. So how many different ways are there of arranging three people in a line? Okay, so let's say we've got three people. Let's say they're people A, B, and C. So in the classroom, I'd probably get three people up, and we would rearrange them to work out how many here. But let's do this in this way. So A, B, or C is one order that they can stand. You need to be systematic about trying to think about these problems. So then if I fix A, keep A there, I could also have C and then B. Alright, let's go back to the beginning where if we fix B in the second position, okay, then we could reverse the C and the A round, okay. Or if we actually, no, sorry, I'm being unsystematic there. So I'm fixing A in the first position. Right, then I think about what happens if A is in the second position. So I could have B and then C, or I could have C and then B. And then if I think about what happens if I have A in the third position, I can have B and then C, or C and then B. So there's 6 different arrangements that can happen, okay? So 6 arrangements. How many different ways are there of arranging 4 people in a line? So again, there's going to be more options, but we still just need to be systematic about it. So if we have 4 people, A, B, C, and D, okay? Now what you might want to think about is, okay, I can use what I learnt in the previous problem, okay? I can think about, right, if I fix A and think about how many different ways can I rearrange B, C, and D, I already know there's 6 different ways that I can rearrange B, C, and D. Okay, so that means that there are 6 arrangements with A at the beginning. Okay. Then if I think about, right, what about if I put A in the second position? Alright. Again, the question is still about how do I arrange these 3 other people around them, and I know from what I learned over here, there's 6 different ways to arrange 3 people. So there are 6 different arrangements I can have of the other people. So again, there's going to be 6 of those. And then if I put A in the third position, there's going to be 6 arrangements of the other 3 people around that. And then if I put A in the fourth position, there's going to be 6 arrangements with A in the fourth position, because the other 3 can be arranged in 6 different ways. Okay, so A can be in the first position, so we've got 6 of those, 6 of those, oh sorry, 6 of those, and 6 of those. Now A can be in the first position, or in the second position, or in the third position, or in the fourth position. So there are 24 arrangements. Or the way we came to that was to think about it was 4 times the number of ways of arranging 3 people. Okay. Then if we thought about, okay, if we were arranging 5 people, that would be the same logic that we just used here. That would be 5 times. So, hang on. So it was, we know that there are 6 ways to arrange 3 people. Okay. Then we know that there's going to be 4 lots, 4 times 6 ways. So that's 24 ways to arrange 4 people. Then we know if we had 5 people, we can again think about, right, we can fix A, and then we've got 4 other people to arrange. So, but we can fix A can be in any one of the 5 positions, and we arrange and there's going to be 24 arrangements for each of those positions for A, because these can be arranged in 24 different ways. Then we could instead put A here. Oops. And these 4 can be arranged in 24 positions. And again, so there's 5 different places for A to go, and so it'll be 5 times 24. It'll be 5 times 24, which will be whatever that is. 100 and... sorry, it's Friday afternoon when I'm recording this. 5 times 24, so 5 times 20 is 100, and 5 times 4 is 20, so it'll be 120 ways to arrange 5 people. Now, if we went backwards from here, okay, we would think about, well, this would actually be, this 6 is going to be 3 times the number of ways of arranging 2 people. Arranging 2 people. Okay, so it'd be 3 times 2. We can either have them A and B or B and A. Okay, and then we can think about, all right, well, the number of ways of arranging, so 2 is the number of ways of arranging 2 people, and 1 is the number of ways of arranging 1 person. Okay, so essentially what's happening here each time, if I wanted to arrange 6 people, okay, I'm going to be doing 6 times the number of ways of arranging 5 people. And remember, the number of ways of arranging 5 people was 5 times the number of ways of arranging 4 people. And the number of ways of arranging 4 people was 4 times the number of ways of arranging 3 people, which was 3 times the number of... So actually, essentially, what we've done to get to this number here is to do 1 times 2 times 3 times 4 times 5 times 6. And this is a special name. This is called 6 factorial. We generally would write it in the other order. 6 times 5 times 4 times 3 times 2 times 1 is 6 factorial. 8 factorial would be the number of ways of arranging 8 people, and that would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, whatever that is. Generally speaking, if we have n objects, people, books, things, whatever, to arrange in a row, there are n factorial ways of doing that. So this sentence isn't, this exclamation point at the end here isn't me being excited about saying that the number of ways of arranging n objects in a row is n. It is n factorial. This exclamation mark is called factorial. So if I wanted to work out what 8 factorial was, I don't need to type in 8 times 7 times 6 times etc. in my CAS. I mean, we can. I'll do it to verify it gives us the same thing. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is 40,320, or I can simply do 8 factorial, and there are instructions here with our CAS. So I'm going to type the 8 first, and then I go menu 5 1 to get the factorial, enter. There is also, I think it's in the pi button down here. No, it's not there. It is in one of the, over here on the right next to the number G. Next to the number G, the letter G, you can get the exclamation point here. But actually, if you know menu 5.1, I find it's quicker to type menu 5.1. Okay, so then example 1, how many different ways are there of arranging 15 people in a line? Well, that will just be 15 factorial. Okay, 15 menu, what did I say it was again? Menu 5.1, enter, and that is a lot of ways. 1 3 0 7 6 7 4 3 6 8 0 0 0. What you find here is you get very rapid growth. Okay, it's a bit like, it is actually exponential growth. You're multiplying by something each time, but it's not technically exponential growth because you're not multiplying by the same thing each time. But you're actually multiplying by a bigger number each time you multiply. So, you know, 14 factorial is however big it is, but then 15 factorial is 15 times as big as that. 16 factorial is 16 times as big as that. So things get big really quickly. If you've got 15 books on a bookshelf and you want to arrange them, there are this many ways of arranging them. I can't even think about what that is in terms of billions, trillions, etc. It's a lot. Okay. Alright, B, 9 different books are to be arranged on a shelf. In how many ways can this be done? Fine, 9 factorial. As simple as that. 9, menu 5.1, 9 factorial, enter. 362,880 different ways to arrange your 9 different books on a shelf. Okay, you can have book A, then book B, then book C, etc. Then you can have book B, then book A, book C, etc. There's 360 or so thousand ways of doing that. This is why it's hard to win the lottery. There are so many different combinations of numbers that can come up. Alright, so they're very simple examples. That's simpler than you're going to get. So what's going to start to happen is we're going to have situations where we perhaps don't need to arrange all of the objects. So let's think about if we had 8 runners competing in a race. In how many different ways could the first, second and third places be awarded? Now I find often in solving these kind of problems a sort of pigeonholing technique is useful. Okay, so we're going to have 1, 2, 3 places that we need to fill in this running race. Someone needs to come first and second and third. So the number of options for first place multiplied by the number of options for second place multiplied by the number of options for third place is going to give me my total number of options. So there are 8 runners in the race, which means there are 8 possible people who could come first. Okay, but then somebody's come first. So in terms of how many people could come second, well, there's only 7 people left to come second. And then in terms of who could come third, there's only 6 people left to come third. So 8 times 7 times 6 would give us 336 different ways that first, second and third place can be filled. Obviously assuming that every runner has equal possibility of winning the race. So I want to think a bit about how we can write this using factorials. Personally, if I was just answering this question, this is exactly what I would write and exactly how I would do it. But I just want to sort of formulate a way of expressing this as factorials. So 8 times 7 times 6 is the beginning of 8 factorial. Okay, so let's think about that. So 8 factorial, we know is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, we don't want this bit. Now, a lot of students go, oh, well, we'll just take away 5 factorial, okay? But taking away 5 factorial, taking away 5 times 4 times 3 times 2 times 1 isn't the same as undoing the fact that you are multiplying by 5 times 4 times 3 times 2 times 1, okay? So, for example, so if I were to then take away 5 times 4 times 3 times 2 times 1, that doesn't cancel out that 5. They don't cancel out. So the way I'm going to be able to cancel them out is not to take them away, but to divide by 5 times 4 times 3 times 2 times 1. Okay, that would then cancel all of that out, and I just get left with, so it's 8, we've done 8 factorial divided by 5 factorial, which just leaves us with 8 times 7 times 6, which is what we want. So if we were to think about that more generally, if we have n objects to be arranged into r positions, okay, in the same way that here we just did an example where n was 8 and r was 3, and we found that that was 8 factorial over not 3 factorial but 5 factorial. And that 5 factorial came from the fact that we wanted to keep 3 positions, so the remaining 5 are what we don't want. And so therefore, as a general rule, that is n factorial divided by n minus r factorial. And this has a special name, NPR. Okay, P stands for permutations. Another word for arrangement is a permutation. Okay, we look at how many different arrangements are possible or how many different permutations are possible. Those are synonyms if you go to your thesaurus. So the rule for NPR is n factorial over n minus r factorial. Okay, so if, for example, in this example up here, this would be the same as 8p3. We have 8 objects to arrange in 3 positions, and if I type into my calculator NP3, so there should be instructions here for where to get NP3, it's menu 5.2. So I type that first, menu 5.2, brings up NPR, and then I simply do 8, 3 if I want 8p3, and that is 336. Okay, so lots of different ways we can express this answer, or calculate this answer. 8 times 7 times 6. Honestly, that's the simplest way. That's how I would do it 9 times out of 10. That is the same as 8 factorial over 5 factorial, which is the same as 8p3. 8 permute 3. I have 8 things to permute or arrange into 3 positions. Okay, and all of those calculations will give me 336. Okay, so 3 books are to be displayed in a row in a bookshop window. If there are 15 books to choose from, find the number of possible arrangements for the display. Okay, so we could say we have 15 things that we want to arrange or permute into, we want 3 books, into 3 different positions. So we could do NP3. Or we could say, well, that's going to be, I've got 3 different positions on my bookshelf, which is, and I've got 15 books that could go in the first position, but once I've put one of the books in the first position, there's only 14 left to go in the second position, and once I've got 2 books, there's only 13 books left to go in the third position. Or that calculation is the same as 15 factorial over 15 minus 3, which is 12 factorial. Any one of those things will give us the same thing. So menu 5.2, 15p3 is 2730. 15 times 14, times 13 is 2730, or 15 factorial divided by 12. 12 factorial is also 2730. These are all the same thing. In all honesty, arrangements, I don't really tend to use this very often. I also wouldn't bother to go to that notation very often, although you might get a multiple choice question that suggests that you need to, which of the following would give the answer. This would generally be my default method, this kind of pigeonholing process. Right, I've got 3 positions. How many options can go in this position? How many options can go in this position? How many options can go in this position? And do I want that, or do I want that and that? So do I add those options together, or do I multiply those options together? And in this case, we multiply. Okay, example 4. How many different 4-digit numbers so it shouldn't be a that there. How many different 4-digit numbers can be formed from the digits 1, 2, 3, 4, 5, 6, 7, 8, 9 if each digit can be used only once, or if each digit can be used more than once? Okay, so I have a 4-digit number, so 4 positions in which to arrange digits. We have a total of 9 digits to choose from. Okay, now in part A we can only use each digit once, which means there are 9 options for the first digit of our 4-digit number, but once one of those 9 digits is already in the first digit position, we only have 8 options left for the second, 7 options left for the third, and 6 options left for the fourth. I want a 4-digit number, so I need to have a number in the first position, and in the second position, and in the third position, and in the fourth position. So 9 times 8 times 7 times 6, which could also be written as 9 factorial over 5 factorial. So that is, or that could be NP4. I'm arranging 9 objects in 4 positions. Okay, any of those things would work. 9 times 8 times 7 times 6, as I said, I would generally just do the first one, work it out, and it's 3024 different 4-digit numbers that can be created. Okay, but this is where these options become a bit limited, and your sort of pigeonholing technique works every time for all sorts of different restrictions. So again, we've got our 4-digit number. We want a number in each of those places, so that, and that, and that, and that. This time we can use the digits more than once. So we now have 9 options that can go in the first position, but then we still have 9 options for the second position because we're allowed to repeat the digits, and 9 options for the third position, and 9 options for the fourth position. So this is just 9 to the power of 4, which we can work out. There should be a lot more options here, which is 6,561 options if we can use the digits more than once. Okay, we might have more restrictions than that. How many different 3-digit numbers can be formed from the digits 0, 1, 2, 3, 4, 5 if each digit can be used only once, and if A, there are no restrictions, B, the number must be even? Okay, I'm going to read this no restrictions with a slight caveat here because the particular digits we've been given create a certain caveat. The fact that we've got 0 here, we need to be cautious about. Okay, so let's just think carefully about what could happen. So we've got a 3-digit number. We can only use each digit once. Now, the problem is, if I want a 3-digit number, this digit can't be 0. Because if it starts with a 0, it's not a 3-digit number, it's a 2-digit number. So we actually only have 5 options, 1, 2, 3, 4, or 5, that could go in the first position. Now, we can't repeat, so we've already put one of the, let's say 3 went in the first position. We now have the 0s back in the running now. We can now have 0, 1, 2, 4, or 5 that can go in the second position. So we still have 5 options for the second position. All right. And then we now have only 4 options remaining. We had 6 digits, we've used 2, we only have 4 options left for the last one. Okay. So it's not going to be 6 times 5 times 4, it's going to be 5 times 5 times 4 because we cannot put a 0 in the first position. 5 times 5 is 25 and that times 4, so there's 100 different numbers we could create with these, 3-digit numbers we could create with these restrictions. Alright, the second option, or part B, is again a 3-digit number, but this time the number must be even. And we actually need to, so now we know this one has to be 0, 2, or 4 to get an even number, and this one can't be 0. Now, we've got 2 restrictions on both the first and the third digit, which both involve 0, and so we need to be a bit careful here. Okay, so we need to think about, because if the 0 goes here, then there isn't a 0 left to be an option for here, and there's 5 options for here. If, however, a 2 goes here, then we've already ruled out the 2. We've got 5 different digits, but one of those is a 0, so there's only 4 different options that can go here. So there's actually 2 different cases that we need to think about separately. Okay, we're going to have a number that ends with a 0. Okay, so if this has to be a 0 here, in the final position, that means that there is only one option for the final position. Okay, but by putting the 0 at the end there, then it means that any of the remaining 5 digits can go at the start, because the 0 is no longer in the mix, and then we have 4 digits left to go here. So there's 20 different 3-digit numbers that are even, and obviously don't have a 0. Sorry, not just that are even, that have 0 at the end. Okay. Then we need to have ends, or it could end with 2 or 4. Okay. So this time we're saying this can be 2 or 4, which means there's 2 options for that digit there. Now, we've put a number at the end. Whether it was a 2 or a 4, it doesn't matter. Let's say it was a 4. We've put 4 at the end, okay? And so now we have 5 digits. We have 5 digits remaining, but one of those digits is still a 0. So only 4 of those digits can go into the first position. And now we've used 2 digits. We've used, let's say I said we used the 4. Let's say we put the 5 in the first position. We now have 4 remaining digits, any of which could go here. And so there are 4 options for here. So 4 times 4 is 16, and times 2 is 32 different options that end with a 2 or a 4. Now, we multiply here because we need the first digit and the second digit and the third digit. We multiplied here because we needed the first digit and the second digit and the third digit. But we could have a number that ends with 0 or a number that ends with 2 or 4. So we're going to add those together, and therefore there are 52 different digits. Okay. Alright, let's have a look at example 6. 4 boys and 4 girls are to be arranged in a row so that the sex of each person in the row alternates. In how many different ways can this be done? Okay, so a couple of different ways to think about this. We have 8, I'm going to do it in a few different ways. We have 8 seats to fill. Let's imagine we've got 8 people, we're going to seat them in a row. We want the sex of each person to alternate. So what have I got there? 5, 6, 7, 8. Okay, so then we could do what we've been doing with the numbers up until now. We need someone in each of the seats, someone in that seat and in that seat and in that seat and in that seat and in there and. So we're going to multiply the options together. How many people could possibly sit in the first seat? We've got 8 people, any one of them could sit in the first seat. 8 options for the first seat. Okay. But then, once someone has sat here, that person is either a boy or a girl, which means someone from the opposite gender has to go in the next seat. Okay, so if let's say a boy went here, then one of the 4 remaining girls would have to sit here. It would be the same if I did it the other way around. If it was a girl that sat there, out of the 8 people, it was a girl that sat down, that means one of the 4 remaining boys have to go here. Okay, so now at this point we've seated, let's say we went boy and then girl, we've seated one of each gender. Okay, so we need to have a boy in this seat. There are 3 boys left to choose from. We then need a girl in this seat. There are still 3 girls left to choose from. We've now used 2 boys and 2 girls. We need a boy in this seat. There's only 2 boys left. We need a girl in this seat. There's only 2 girls left. Okay. We then need a boy in this seat. There's only 1 boy left, and a boy in this seat. There's only 1 boy left. So 8 times 4 times 3 times 3 times 2 times 2 times 1 times 1. 8 times 4 times 3 times 3 times 2 times 2 times 1 times 1 is not going to do anything. So there is 1,152 different ways these 8 boys and girls can be seated so that their gender alternates. Okay, the other way that we can think about this is we can think about, alright, let's say we're going to have girl, 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 and I'm sorry to gender stereotype with blue and pink boxes. Well, it's slightly purple. Alright, but just for the purposes of illustration, we're going to have 4 boys and 4 girls alternating. Okay, so in the girl seats, there are 4 factorial ways to arrange the 4 girls in those seats. Okay. In the boy seats, there are 4 factorial ways to arrange the boys in those seats. And then there's one other thing I need to think about, because I drew the diagram starting with a girl, but we could have, so if it starts with a girl, there's 4 factorial times 4 factorial different ways of arranging, or it could start with a boy. So then if we think about, well, there are 2 different ways to do this, because we could then just switch around the blue and the purple seats. And so the other way that we can calculate then is, it is 4 factorial times 4 factorial times 2, okay, which should still give us 4 menu 5 1 times 4 menu 5 1 times 2, which should still give us 1 1 5 2 different ways of arranging the boys and girls. Okay. Essentially, this calculation here, if we have a look at it, okay, we can see, if I think about, okay, well, that's a 4 times 3 times 2 times 1, that's the 4 factorial for arranging the girls. And if instead of writing this as an 8, I write it as 2 times 4, then I've also got the 4 times 3 times 2 times 1 different ways of arranging the boys, and then doubled. Okay, so it is the same calculation. The numbers are being put together just in a slightly different way, just thinking sort of in a slightly different logical way about it. Alright, example 7. In how many different ways can 4 boys and 4 girls be arranged in a row if there is to be a girl at each end? Okay, so this time we've got a girl at each end, a girl at that end, then we're going to have 1, 2, 3, 4, 5, 6 people in there, and a girl at the other end. Okay, so there are only 4 girls, which means there are 4 people that can sit in that seat, and therefore only 3 people left that can sit in that seat. Now, there are no restrictions at all on what can happen here. So these 6 people can just be arranged in 6 factorial different ways. It doesn't matter how they sit. The key is to deal with the restrictions and then think about what's happening with everyone else. So we've got 4 times 6 factorial times 3, because we need someone in each seat. So it's that seat times times. So 4 times 6 factorial times 3 is 8,640 different ways to arrange the 4 boys and 4 girls if there has to be a girl at each end. Alright, example 8, the final one. How many numbers greater than 500 can be formed from the digits 1, 2, 3, 4, 5 if no digit can be used more than once? Okay, so the key thing you need to think about here is it's just numbers greater than 500. It doesn't say 3-digit numbers greater than 500. So we want to think about, we can have 3-digit numbers that would be greater than 500, or we could have 4-digit numbers, or we could have 5-digit numbers. Digit. So we're going to work out how many different 3-digit numbers are there, add that together with the number of 4-digit numbers, and add that together with the number of 5-digit numbers. Okay, so 3-digit number. We need a number in the first position and the second position and the third position, so we're going to multiply them together. Now, if the number has to be, if the numbers have to be greater than 500, we must have a 5 in the first position. So there's only one option for the first position. And then we can't repeat the digits, so we've already used the 5. There are four digits remaining that can go here, so 4 options for the second position. We've now used 2 out of our 5 digits, so there are only 3 digits remaining here. So there are 12 different 3-digit numbers greater than 500. Then we want to think about the 4-digit numbers. Okay. Now, every single 4-digit number is bigger than 500, so any of the 5 digits can go here, any of the 4 digits can then be left to go here, any of the 3 remaining digits can go here, any of the 2 remaining digits can go here. 5 times 4 is 20, times 3 is 60, times 2 is 120. Okay, or we want a 5-digit number. Okay, so there are 5 digits that could go in the first position, 4, 3, 2, 1. Interestingly, that's just the same as the previous answer multiplied by 1, so it's still also 120. And that's because if you've arranged 4 of the 5 digits, then there's only 1 left over. So if you're going to just tack another number on the end, there's not it's still the same number of arrangements that you can get. Okay, so then we want 3-digit or 4-digit or 5-digit, so we're going to add all those together, and we find that we get 252 different options. 252 different numbers that are greater than 500 can be formed from the digits 1, 2, 3, 4, 5 if we can't repeat the digits. Alright, so the work today is from exercise 10B.